I do want to take a minute to go through the session outline. What exactly do we want to accomplish here? What are we going to gain out of this workshop? What exactly does just enough software look like? Can we put up a small piece of software and say, yep, that is just enough? And what is it just enough for? We're going to review the idea of a software stack and why that's important. And then we'll spend quite a bit of time on the hands-on portion of this exercise, working through the hardware that is sitting in front of you right now. We'll then take what we just learned and apply it to other just enough software examples, targeting different platforms, FPGA platforms, different processors, and some NoOS examples, and how do they relate to the experiment that we've just done. And we'll also draw parallels to other software development flows. This is a workshop, so it's not a unidirectional presentation. Although if you're listening to this, this is a recording. But we'll have my co-presenters or the co-presenters out in the audience as well. So we'll have time to methodically work through the hands-on exercise as well as take some questions. Give us sort of real-time feedback here. We'll be taking notes. So a little slide on recommended preparation. I stole this from our 2019, one of our 2019 workshops here. I did say in the abstract for this session that you don't need a deep knowledge of Python. We'll be using it as a tool, but you don't need to know much more than Hello World to get the basic idea. I definitely encourage you to dive deeper, though. And here's just a couple of resources here. LearnPython.org. Python for Kids is surprisingly good for adults. And there's quite the ADALM 2000 and the ADALM Pluto. Those are all Python friendly. So there's there's some simple Python examples for wiggling outputs and receiving data and things like that. Lots of tutorials. There's a couple of tutorials written up on the wiki, and towards the end we'll have some information on further learning resources. We will also have contests with prizes. So there's two contests that we'll be having through the workshop. One is hidden based on an observation that one of our reviewers made. So keep your eyes out for just an interesting little nugget worth pointing out. And who knows, maybe it is the hidden contest and you'll win a prize here. And we'll also have an explicit contest. We'll have a little programming exercise, and the prize is this cute little discrete op-amp board designed by Analog Devices fellow Doug Mercer, who contributes heavily to the university program here. And if you don't want the discrete op-amp, then find someone to give it to. Smart kid, new college grad, your favorite teacher or professor. Again, this is also written up on the ADI Wiki. So what are our objectives here? So through a hands-on example, explore hardware and software tools for accelerating customers' prototyping and proof of concept phases. So what we mean by that is going beyond just a basic evaluation board, going beyond capturing an FFT plot in ACE or something like that. What is the next step that we can help our customer with? We're going to build familiarity with device drivers, less so with the drivers than with their examples. Little simple examples that show the driver in action, both in hardware and software. We'll learn about some tools, and we'll use some Python scripts to, again, make little applications that are one step beyond these basic examples. Let's head the customer down the path from, in addition to just capturing data from an ADC or sending data to a DAC, what's the next thing that we can do for the customer to help them down their path? And just a little anecdote here, getting a customer to Hello World with the new part is a critical point in the process, so it's worth spending some time here. We also have some unobjectives. We won't be building Linux kernels. We won't be writing full-featured fancy GUIs from scratch or anything like that. I personally avoid GUIs like the plague. I almost never write them because I'm terrible at it. I'll use simple plotting routines, but anything beyond that, I'll fall back to some other plotting routine, etc. I do almost everything just as dumb command line scripts with basic debug information. I want to prove the concept out and then leave the window dressing or the more intuitive graphical interface to someone who actually knows what they're doing. Okay, a couple little anecdotes here, and I promise this is the last text-filled slide that we'll have here, but I do want to kind of read these out loud. We tried to collect quite a bit of feedback before putting this session together to make sure that we were on track, and one very experienced FAE who services a well-known computer manufacturer put it this way, that the biggest challenge is convincing hardware FAEs that you need very little knowledge and commitment to support these simple software tasks at the customer. There's a fear, like when speaking a language for the first time, that if you speak, you won't understand the response. And that's kind of an objective of this workshop. We want to get you just familiar enough to feel comfortable in those conversations. You don't have to know everything, but you should feel comfortable asking questions and turning turning the answers into something actionable. Another little anecdote here from Joseph Spencer was this idea of tearing down the wall of the customer's software department, meaning don't give the software department a reason to block. If you show a software engineer a device driver, a working example running on hardware in front of them, it's a really effective weapon. In the old days, analog engineers had the say. Nowadays, the software engineers, a customer software department has veto power. If a device doesn't have a well-written and documented driver, a software engineer can say, nope, we're not using that part at all. Okay, so what exactly does just enough software look like? And let's take a peek at an example here. So maybe some of you recognize this little widget here. This is the CircuitNote 503 optical liquid analysis platform. I kind of joke that this is the simplest electrically and most complicated mechanically circuit note that we've ever done. All it really is, it's an ADPD 4101 photometric multimodal front-end chip with a bypass capacitor. And that's it, sitting underneath this 3D printed platform here. So this thing comes as a kit with a bunch of photodiode boards and a rather elaborate mechanical assembly here, liquid cuvette holder with lenses and beam splitters and things like that. So very complicated electrically here. And the software that goes along with it is pretty complicated as well. We put together a GUI that allows you to run a couple of different classes of applications. But how do we give the customer the ability to move beyond those basic examples and start morphing it into something that's meaningful for their end application? And so after releasing this board, we sort of rehashed the software and we re-architected it in a way where the device driver is running on a platform board here, and it's acting as a little server that allows you to connect a remote PC to the device here. And we're going to dig into this in a lot more detail, but the end result is I can write a complete application for this board in just a few lines of code here. So we'll learn more about what import ADI means, but if we trace through this code here, my ADPD 4100X, yeah, it sounds childish, but I like to preface my things with that represent a physical piece of hardware that's in front of me. That's how simple-minded I am. So I'm going to create an instance of an ADPD 4100X, and I pass this connection function the serial port number of my board here. So it shows up as a virtual COM port. And then from there, it's a matter of taking, for example, a reference reading. In the case of the CN503, that may be the output from the beam splitter. So I send the beam through a beam splitter, I measure its intensity, and then I have an active reading that actually passes through the liquid. And that is represented by reading here. That's simply channel 0 and channel 1. And then I can calculate my measurement by passing those values to my formula. What do these do? You know, who knows? That is for your customer to tell you. Maybe it's a simple division. Maybe there's a more elaborate formula there. Maybe you also need to pass in temperature to compensate for the temperature drift of various elements here. The point is, if you can boil things down to this level, customer, what do you need to do with the ADC readings to turn it into a reading that means something to you? Sketch it down as a formula, translate it to Python, and then go to town. So print out my measurement, and you get the idea here. So we've taken a complicated, elaborate board, boiled it down to a few lines of Python code, hopefully allowing the non-computer science subject matter expert to get to work, measuring quinine or measuring pH or something like that. Couple little nuggets here is the idea is to distill applications to the bare minimum software that demonstrates the principle and the parts value proposition. Is the GUI color scheme important? Probably not. You can ignore it. Is the shape of the enclosure important? Probably not for now. And the CN501 kind of illustrates this. Notice that this is not in an enclosure. This part, the light sampling scheme of this part, rejects ambient light very effectively. So the fact that this is not in an enclosure is actually part of the value proposition here. And if I wanted to script this up, take readings and control the intensity of an interfering light to prove that to myself in a programmatic way, I've got all the tools that I need. Okay. If you think that there's a lot that simple program was hiding a lot under the hood, you'd be absolutely right. So it is true that that simple Python snippet relies on quite a bit of software under the surface here. And a diagram like this is really helpful to sort of understand how the pieces fit together. And let's just take a minute to walk through this. So obviously, at the very lowest level, I've got an ADC or a DAC, some physical device of some sort. And ideally, I'd phone up the product line apps person, and they would help me choose a device. That will then connect to the physical platform board. If it's a microcontroller, then the SPI or I2C port is built into the device. If it's something custom, like an LVDS interface or a JESD interface, then an HDL engineer would be involved. Next layer up, we've got platform drivers that drive the peripheral, device drivers, and then in the case of a Linux system, you've got files in the system file system, and a lot of things that you probably don't need to understand to write a basic application. But if you can do all of this in a standard way and boil it down to sort of a common interface, then there's a place here where you can add lots of value. This is where the rest of us can start to add value. If we can write simple Python or MATLAB or C programs to get the job done, it's helpful to know what's going on underneath the surface here, but it's not important to understand all of the details. And then if you can put this together and spit out accurate numbers to a command line interface, then your customer software department can take those numbers, put them up in a GUI, and vice versa, take control functions from a GUI, pass it down to the hardware, and so on and so forth. So yeah, it's a deep stack with a lot of layers and a lot of moving parts. But again, if this is done properly, then there's a place where normal human beings like the rest of us can write software to do something useful. We are not going to get too much into what libiio is, but we're going to study PyADI IIO, and that's what we'll be using to talk to our hardware. Okay, so that was a thick slide with a lot of words around it. And it does take some effort to understand these things, but a key concept to keep in mind is that this workshop applies broadly. So we're not just talking about photometric front ends or the little contrived example we'll look at in a minute. Coincidentally or serendipitously, as I was putting this slide deck together, I got a promotional email from the instrumentation group here. And I looked, and all three of these devices are cleanly supported in this same framework that we'll be looking at. So what that means is for 4630, rocket science. This thing is the most linear A to D converter on the planet. It's being heavily promoted. Well, guess what? You can write just enough software for this. It is possible to boil down connecting to this part, setting up parameters, capturing data, and calculating a result based on the customer's analysis function and doing something useful. Same thing with AD3552R. Very nice D to A converter. I've been wishing for a part like this for a long time because it's a very nice replacement for an ancient linear technology part. Again, I can connect to the part. I can create samples based on a customer waveform generator. Maybe it's not a sine wave. Maybe it's a wavelet. Maybe it's a seismic waveform or something like that. We don't have to know. If the customer can describe what it is, then we can put it in a buffer and send it off to the DAC. And then finally, LTC2387, a part that's near and dear to my heart. Very nice, very linear device that is being integrated into modern micromodules. So even though this part is probably pushing 10 years old, it is still shows up in promotional material now, and it's still being heavily promoted. Okay, so all of these parts are cutting edge enabling technology. But let's warm up with a definitely totally not contrived case study here. So now we're heading towards the hands-on portion of our workshop here. So you all have heard of Keysight and Fluke and Tektronix and maybe Rohde and Schwartz. Those guys had better look out because Fred in the Shed Instruments is in business. So this is an up-and-coming test instrument manufacturing company, and their first product is this CT001 curve tracer. So this is an analog circuit for measuring transistor parameters, and let's assume that that's Fred's domain. You know, he knows what he's doing in the analog domain here. So we're going to help choose an ADC and a D to A converter. We'll walk the customer through the proof of concept and then provide several paths towards production. Okay, and photo credit here, I stole this from a very nice Instructable. As I was making this slide, I could put together a little sketch of something on my own, but sure enough, I figured someone must have made a pocket curve tracer, and yeah, the answer is yes. So check out this guy's this guy's little hand-built curve tracer here. Neat little project. Okay, so let's take a look at the analog circuit. So a curve tracer is it measures semiconductor parameters. It sweeps, sweep a voltage, look at the current, step the base drive on a bipolar transistor, or step the gate voltage on a MOSFET. And so we'll start out with the most common transistor on the face of the earth, the 2N3904. So we'll take a minute to see what we're doing here. This is an initial prototype, so we're not going to use an actual current source for the base drive. We're going to drive a voltage across a fairly large resistor to generate our base currents here. We'll assume that VBE is fairly well behaved at 0.7 volts or so, and we'll drive a collector drive voltage up to the collector, but we want to keep things really simple. So we're going to park a sense resistor upstairs here, and we'll measure the difference between VC drive and VC sense to calculate the collector current. And sure enough, if you run this LT-SPICE simulation, you get a pretty good picture. This is just like something you would see on your old Tektronix curve tracer here. Notice that we've got a little bit of a slope at the endpoints here. This is the voltage that is dropped across the sense resistor. So hopefully all of the analog experts in our conference room here today know this sort of thing like the back of their hand. It's a really simple analog circuit, and we're going to build ourselves a machine to take measurements with it. Okay, so let's start seeing where these pieces fit together in the stack. So obviously we've got our analog circuit down here. We need to drive voltages, we need to measure voltages. And again, we'll phone up the product line apps engineer for help here. Now, all of this other stuff in between, where we want to talk to this device in as convenient a way as possible. Well, if we pick the right part, then ideally this stuff is already done. We don't need to worry about it. We shouldn't have to worry about things at this level here. And if we do that, then the rest of us in this room here should be able to write simple little applications to draw out draw out our curves here. And then once we're at that level, we can say, hey, customer, the concept is proven. Now you can pass this over to your GUI designer. So let's pick an A to D or a D to A to D and a D to A converter here. So where would we typically start for that? But a better question is, where would the customer start? So, again, in the old days, in finger quotes, the analog engineer had the say. I need a part with the best performance. I need 16 bits, or I need 24 bits, or 18 bits, that's my line in the sand, and I'm picking the part. But of course, analog engineers are becoming less and less common, and software is taking over the world, and the software engineers have much, much more say, if not the final say. So a common situation is that a customer software department, if a project is Linux-based, they will insist on the device driver being upstreamed. So I took a little screenshot here from kernel.org, and we should all recognize some of these parts here. AD7124, 7606. We've got a SAR ADC and a Sigma Delta ADC, and this is just a small portion. And you can, worth pointing out is that these show up in a directory called IIO/ADC. There's a separate folder for DACs and for gyros and for accelerometers and things like that as well. So more and more, your customers will say, okay, fine, analog engineer, you picked your part. If it doesn't show up over here, then I'm going to veto it. Okay, so back to the Fred in the Shed curve tracer here. So let's say that we want to leave room for future expansion here. Let's say that we want to build a core analog circuit and have it function as a curve tracer and maybe a signal source and maybe a general purpose multi-channel data acquisition system. And what better part for that than the AD5592? It's not the highest performance A to D or D to A converter, but boy is it cool. It's got 8 D to A converters, an 8-channel multiplex SAR converter, and it's basically got a crossbar switch. Any I/O pin can function as a digital GPIO or an analog GPIO, so super versatile part. And on top of that, a Linux driver exists, and of course it's documented, and same thing with no OS. So we can take this device and, in theory, talk to it from a Linux-based machine like our Raspberry Pi, and then when we're done with that, we can move over to an embedded solution. And in theory, we've got the drivers already. We don't have to reinvent the wheel there. Okay, so moving on to the hardware portion. So we're finally going to start getting our hands on some hardware here. So a quick little overview of the setup here. So this is a Raspberry Pi 400. Anyone who's tried to buy a Raspberry Pi in the last year probably knows the frustration that we're going through here. It's very hard to get these things. I think I may have bought up the last 25 Raspberry Pi 400s on the planet for this workshop here. It was like the last one that you could get. But that's pretty convenient for this workshop because we've got the keyboard, we've got the official Raspberry Pi mouse. We spared no expense, a whole $8 for each one of these things. And I guess the biggest advantage here is you guys don't have to install any software on your machines. So everything is going to run on this Raspberry Pi. However, it can easily be migrated to another embedded Linux system or something like that. It just happens to be a representative Linux-based system. Little ribbon cable out to this little adapter board here. So this is a released adapter. It's intended for developing with peripherals. We've got 2 SPI PMOD connectors, 2 I2C connectors, and the legacy linear folks in the room will recognize the quick eval connector and the quick eval and the PSM connector here. So these should all be set up on your bench here. hardware connection is really simple. We're just mapping the SPI port from the Raspberry Pi peripheral connector over to the PMOD connector, and that is done through this RPi PMOD interposer board here. And worth pointing out, this is why we're not using your laptop for talking directly to this device, because a typical laptop or a desktop PC doesn't have an exposed SPI device on it. So in contrast, Raspberry Pi is intended for embedded hardware development. The astute will have noticed that we're only using one device here, only one of the 6 connectors on that board. So just a little reminder that, yeah, there's a lot of other stuff here. So by the time we're done with this workshop here, you should be armed and dangerous to play around with AD7124, ADXL355, 2688 DAC, the Linear Tech Power Stick. What else do we have here? Capacitance to digital converter, and the I2C version of the device that's in front of you, the AD5593. So I forget the count on this. We've probably got 20 or 30 peripherals. And if they're not already tested with the variant of Linux that we're running here, it's in progress. So again, just intended for hardware, intended for prototyping with these devices. And you'll notice a little pin remapping matrix up here in case there's some conflict with between devices here. So again, and you'll notice that I still have a reminder up to retake this photo. Okay, so let's talk about ADI Kuiper Linux. So this is our own variant of Raspberry Pi OS. And again, this was sort of conceived back around the 2019 timeframe. Mircea Cepriaru in Romania had done a first variant of that. And so why did we go through this trouble? And really the reason is so that you don't have to go through the trouble to build kernels and fight with FPGA toolchains to get off the starting line. So it's the intent of Kuiper Linux is not to take a customer all the way to production. It's to get to hello world with a part. Get up and running in 5 minutes or less, and your customer can customize HDL or software or etc. at a later time here. So it's really getting to that proof of concept, initial signs of life thing. It's released. It's got a landing page. It is definitely not a toy. All of the projects are in a continuous integration test flow. There's a board farm in GT. So as we're working through this example, know that there's a lot of rigor behind it here. It is also being used for product line evaluation boards. The AD4630, this amazingly linear ADC, is sort of the flagship. And go talk to Michael Bradley out on the expo floor there. He's the one that's really driving this. So what that means is a single hardware setup with a 4630 on a Z board functions with ACE, the eval tools that you're familiar with, as well as the environment we're talking about here. Lots of other GUIs that we'll be exploring here, and again, so worth exploring a little bit more as well. Okay, so let's turn our attention to the screen in front of you here. So all of the machines in front of you should have been pre-booted. They should have been booted up already, and you should see the Kuiper Linux desktop here. And so the first thing that we're going to do is open up a terminal. And there's a terminal icon in the toolbar here. So open up a terminal, and I've got a little test command here, who am I? But type in IIO_info and then enter. So don't type this out, but hit the enter key. And what you'll see is I see some information about some devices here. And what do I see here? I see the CPU thermal. So this is actually the temperature sensor that is on the processor, on the Raspberry Pi's processor itself here. And it's in milli-degrees centigrade. So the one here is sitting at about almost 38 degrees, so a little bit warmer than room temperature here. If anyone has played with a Raspberry Pi and used a cable that's a little too skinny, you might have seen a warning pop up in the corner of the desktop saying, warning, low voltage. Well, that information comes from and it comes from a hardware monitoring device that is exposed in the same way as the temperature sensor here. And then we've also got a trigger that's not being used here. So I guess we'll dwell on this for just a minute because we're about to, we don't see our device here yet, but we do see things that are completely unrelated to anything that Analog Devices does. And it's worth pointing out because that sort of drives home the point that this is not an Analog Devices invention, this IAO framework here. It's an industry standard framework, and we're just, we contribute to it, we contribute to reviewing and sort of steering it, but ultimately it is controlled by the larger Linux community. And that should give customers confidence that it's not, these drivers are not something that we just write ourselves, that we're pulling out of thin air. They're peer reviewed and they are part of the mainline Linux kernel. So take a minute to run through this command here and run it a couple of times, and you might see the CPU temperature vary around a little bit just to random variations. Okay, so we ran that command called IAO info. Well, what in the world is IAO? So IAO is the Linux kernel industrial input-output framework, and I should give credit to this slide from Michael Henrich. I stole it from his GRCon slide deck here. And it's not really just for industrial I/O, it's for all non-human interface device I/O. And that's a lot of different things. It's ADCs, DACs, transceivers, light, pressure, angular momentums, frequency synthesizers, even microwave beamformers. So I don't see that listed in here. So another esoteric thing. So it covers a broad class of different devices here. It's been part of Linux for more than 10 years. And the thing worth pointing out here is that there is a cross-platform libiio library with lots of language bindings. So that means, sort of implies that when you're in this universe, when you're looking at these I/O devices, the potential is there to develop on Windows, Linux, Mac in multiple languages here. So again, very powerful compared to a bespoke one-off driver that is done in C only, for example, where it takes an awful lot of extra effort if you want to switch over to C# or MATLAB or something of that nature. Okay, so we didn't see the AD5592 when we ran IAO info. And the reason is we didn't tell Linux that we didn't tell Linux that the device itself was there, and that is the next step in the workshop here. So we're going to open up a terminal. We're going to enter this command. So we're going to cd into the Just Enough Software library, and then we're going to use a little program called Mousepad. We're going to edit config.txt. We're going to uncomment the line at the very end here. And by uncomment, I mean take out the little £sign and the space here so that it reads DT overlay equals RPi, etc. here. And then we're going to copy that file into the boot partition. We're going to enter in, with this command, sudo, we're going to enter the super duper secret password, which is analog. Don't tell anyone, it's super duper secret, and then sudo reboot. So I'm going to go through that process on my end here, just to show you what it looks like. So we'll open up a terminal, and we will cd JES and then tab, and then we're going to Mousepad, config, .text. Okay, that brings up our little text editor here. And while we're editing, take a look at some of the other stuff that's in here. So this particular file format is unique to the Raspberry Pi. Different platforms will have different boot methods, different configuration files, etc. But the basic concept is there. We have certain things we need to configure, like video modes, what peripherals are enabled, etc. And you may notice that the little power light on the Raspberry Pi is blinking. when you first boot up a new Kuiper Linux installation, the little light doesn't blink. There is a set of functions that are available through config, or there's an overlay that will enable the heartbeat. There's also a feature to make one of the GPIO pins as a shutdown. So that's, again, super handy if you're developing. I want a way to shut down the board. Let's say if my display fails to come up or something like that. So again, super handy features here, and put a little description here. So let's go here and delete these two lines, and I'm actually going to leave it. I'm going to leave it undeleted on mine, but from here we'll go File, Save. So pretend that that I didn't do that here, and I'm going to say, you know what? I'll just go ahead and do it. We'll save that, and then from here sudo cp for copy, config.txt, boot, and then super secret password. Okay, and just to make sure that I got that right, we can use a command called cat boot config.txt. And sure enough, at the very end, I see that line uncommented. Okay, so we've told the Raspberry Pi, or we've told the kernel that our device is there. So we've enabled this entity called a device tree overlay, and let's see what that is. Okay, great. So we've told in theory the Raspberry Pi that the device is over there, and we did that by enabling a device tree overlay, or telling the kernel to use a particular overlay. So what exactly is that? I guess a primer on this slide, because it's a lot of text here, is as an FAE, or as a normal human being like myself, normal meaning not computer scientist. I mean that in a good way. You don't need to know all of this from scratch. If you peruse the Engineer Zone Linux device driver forum, you'll see all kinds of questions and answers on device trees. So we provide lots and lots of little snippets and examples, and there is documentation on the Linux device driver page for these things here. But I have rarely built one up from scratch. I'll typically modify examples, and when they get too complicated, I beg for help from the experts here. But it's very helpful to know what exactly they do. So think about a SPI or an I2C device. There's no real way to actively probe those devices at runtime. So, and I think that is said here. Yeah, it describes device information that cannot be dynamically detected. So that's in contrast to like a USB device, where there is an auto detection. There's auto detection functionality there. So a little bit of terminology. A device tree is a human readable text file, and there's a little tool called the device tree compiler that turns it into a thing called a device tree blob. And certain systems like the Raspberry Pi support overlays. So the idea of having a single device tree that describes memory addresses, where the Ethernet port is, where the USB port is, and things of that nature, how big the RAM is and what its addresses are, versus devices that we add ourselves. So it's sort of a hierarchical structure. And then a little snippet here, just to take a look at what sorts of things are in a device tree overlay. There is the SPI bus that I'm connecting the device to. And again, this matches up the hardware that is in front of you. And in this case, we're looking at an ADF 4159. So that's a frequency synthesizer. So a few strings to describe which driver to bind, which chip select I have connected it to. So quite literally, if I unsolder the wire from the Raspberry Pi's chip select 0 and solder it to 1, I would make a corresponding change in the device tree overlay, and lo and behold, it should in theory work. This is also where we tell the where we tell the driver how fast to drive the SPI clock. So I guess the question might come up, why don't I just run as fast as possible all the time? Well, there may be times when, let's say I've got an optical isolator or some other digital isolator, or I've got long runs. I purposely need to run a little bit slower. And of course, this is up to the maximum supported by the device itself. And then beyond that, it's extra properties. What, in the case of a synthesizer, what frequency do I power up at after I throw the power switch here? So again, it's a human readable text file, and yeah, just a human readable text file that describes the hardware that's connected. Okay, so now that Linux knows that the device is connected, let's start poking around at it a little bit. So let's go back to your terminal that should be up in front of you and rerun that IIO info command and see who's home. Then we're going to run a tool called IIO Oscilloscope, and it's shown here on the slide. We'll go to the little start menu here. Under Other, there is this tool called IIO Oscilloscope. And this is a very generic program for communicating with and sort of kicking the tires on IIO devices. It's not intended as a full-featured GUI. It's more of a debug and get started tool, which is exactly what we're doing here. Again, it's still very handy if you've got a new device and you're waiting for a fancy GUI to get written. This is a way of at least getting some data into and out of the device. So we're going to open up IIO Oscilloscope, and you'll notice that two panes show up. One is a plot pane, and we don't have any streaming data coming from this thing, so you can go ahead and close out of that. And then, as it clearly indicated in the slide here, play. So poke around at the values, see what's available under the device window, and it's a little bit cryptic at this level. Things are symbolically named. It's still not as clear as you'd like it to be, but again, we're building up our knowledge here, and by the time we get to our little Python example, things will be an awful lot clearer. Okay, there's a schematic here. There's a bicolor LED connected between out 2 and out 3. So see if you can make it light up. So if you drive one output value to 0, the other to 4095, and then reverse, then you should see that little light blink here. And if you have a meter, then measure the output or see the presenter's meter here. Okay, so let me go ahead and do that on my end here. So let's see. So the first instruction there was to rerun IIO info. So let's, okay. And there's a lot more stuff that showed up here. So in addition to the CPU thermal, and I'm about at the same temperature, a few degrees warmer here, I've got the RPI voltage, under voltage monitor. And here I've got my AD5592 device. And what we see here is we've got various channels available. We've got, and remember that chip, any channel can be an input or an output or both. Analog input, analog output, or both. And so what I notice about channel 3 is that it's an input and it's also an output. So I can write a voltage to channel 3, I can read it back. Channel 2 is just an output, so I can write a voltage. I can read back the value that I've sent to it, but I can't actually read back the analog voltage. All right, so I can write to the DAC, I can read back the value that I wrote to the DAC, but I can't monitor that voltage with the ADC. So, again, take a minute to study what's going on here. Each channel also has a scale value. So this is number of millivolts per LSB, and then scale available value. So in this case, we've actually got two different gains available on both the ADCs and the D to A converters here. So you'll notice that it's a 0.6 millivolts and 1.2 millivolts per LSB. And then let's see, and we're set to the lower one in all cases here. Okay, and then the next step is to open up IIO Oscilloscope. So we'll go to Other. And it's asking for the password. And the reason it's asking for the password is you as a regular user don't have permission to write to hardware devices. And so running this with elevated privilege gives us the ability to write out to values. We can read all we want as a plain old user. It's the writing that is that's prohibited. Okay, again, if we were looking at a Pluto or one of the other transceiver chips or a high-speed A to D converter, then this pane would come into play. But that's not the case here, so we can just close out of it. And let's see who's home. So take a few minutes to explore this pane here. So if we go to the DMM panel, or digital multimeter panel, is basically readback of all slow unbuffered devices. And sure enough, I see that and actually I forgot to mention this, or maybe you noticed it in IO info, the 5592 has a temperature sensor on board. So if you make sure to ground yourself and on the desk there so that you don't have ESD discharge, maybe put your finger on the 5592 and warm it up a couple of degrees. In this case, apparently I've preset the output voltages. So let's go back and set them again. Okay, so I'm going to select the AD5592, and you'll see that I've got several inputs and several outputs. So I wanted to blink the light, so I'm going to go voltage 2, and I'm going to set voltage 2 to 4095, and we'll write that value. And then I'm going to set output voltage 3 to 0 and write that. And I've actually got a multimeter attached here, so hopefully Camtasia catches this here. And sure enough, my LED is green. Okay, so now let's try the other opposite polarity here. So on voltage 3, I'm going to write 4095. I'm going to write that. And if I bring the camera over, my LED is no longer illuminated. And then we'll go over and select channel 2 and change that to 0. And we'll write that value. And then sure enough, we have a red LED. A red LED, and my meter is showing about 2 volts here. And why isn't it 2.5? Let's see. So output voltage 3. Let's double check here. Yeah, 4095. Yeah, it's probably being loaded down a little bit by the LED circuit there. But again, you get the basic idea here. And actually, yeah, it's drifting around a little bit more than I would expect. So maybe that's my meter. You'll notice I spare no expense. We're using this super high quality meter here. Okay, so that is IIO oscilloscope. And so let's go back to the presentation here. Okay. Oh, and also note that if you're trying to think of I'll put here. Oh no, I guess that's it on this slide. Okay, so let's go back to the device tree a little bit here. And again, this is getting a little bit deep. We're going to dig a little bit deep here just for the sake of an understanding here. Let's look at the device tree for the actual device that we're looking at. So this is the device tree overlay that is on your card right now. It's been compiled. That's the one that we enabled here. And just a little reminder where the device tree acts. So it's sort of, the device tree tells the driver which attributes to populate and certain configuration information. And what we see here is things like I'm setting channel 0 mode to DAC. That results in an IO attribute of a voltage 0 output only. In contrast, if I look at channel 1, that is an ADC, and I get a single input. And channel 2 is a DAC and ADC, so I get an output and an input. So I guess the takeaway from this slide is if you, as a non-computer scientist, had to had to go in and change a configuration around. It's possible to do. Again, there's a lot of stuff. There's a lot of other information here that you may want to beg for some help from an expert. But again, the basics are fairly easy to understand. And at the same time, it's easy to reverse engineer this. So if you had an issue that you were debugging, at least you would know enough to go back and say, hey, this is not configured properly. Maybe go in and rebuild your device tree to correspond to how your actual hardware is set up. Okay, and then again, if you're looking to dig deeper, a couple of resources to those ends. Okay, so as wonderful as IO Info and IIO Oscilloscope are, we're going to want to control things programmatically at some point. The sooner the better. And so and we said before we're using Python, and so consider that sort of a toolbox a toolbox item. So I guess this would be maybe a good point to ask who in attendance here has a favorite Python environment. I personally like to use Anaconda. I discovered it years ago, and I've sort of stuck with it ever since. Although I hear that I don't want to say cracking down, but they're making it less free for corporate use. It's still absolutely free for academic and personal use. And a note here that the cool kids use an environment called PyCharm, and the coolest kids use Microsoft VS Code. It also comes pre-installed on Mac and Linux quite often, and there's also Jupyter Notebook, another variant. And actually, go see there's a demo out on the demo floor of the LTC 2387 that is being run in a Jupyter Notebook. It turns out that seem like too many choices, there is already a minimalist Python IDE that's already in Kuiper Linux, and that's what we'll be using in the near future here. So, yep, it comes with a cute Python IDE called Thani. You get variables and breakpoints and things like that. So minimal yet functional for simple programs. Okay, and on top of Python itself, there's a Python abstraction layer that, I guess I'll just read this out here. It's PyADI IIO is a Python abstraction module for ADI hardware with IIO drivers to make them easier to use. That is an understatement. The little snippet of code here is what it is. It takes 3 lines of code to connect to an AD9361, the transceiver chip that's in the Pluto, and grab a block of data. And then after this point, you can take FFTs, plot it out, etc. So it makes it really easy to make that initial connection to a device. Sort of think of it as a glue layer between IIO, this underlying structure, or this underlying API that's a little bit obtuse, and doing something useful here. And of course, it's pre-installed on Kuiper Linux. Okay, and again, just another comment here. If you're working in Python, coupled with things like NumPy and SciPy and other modules, it's really easy to throw something together. Excuse me. It's ridiculously easy to throw together stuff for data generation, capture, analysis, automated testing, and things of that nature. Okay, so what does PyADI IIO look like for the AD5592R? So you might have already picked up on the fact that you create an instance of a device, and you do that by, you instantiate a device by taking the library function or the 5592 class and passing it this thing called the URI, or a uniform resource identifier. And what you put here can vary depending on your vantage point. If we are running on the Raspberry Pi, we can use what's called the local backend. So my program is running on the Raspberry Pi. Therefore, I want to talk to this device that's local on the machine. I can also talk over a network connection. And if I tell this IP localhost, it means, yes, the device is on my machine, but I still want to talk over a network connection. And that's pretty convenient because it gets around some permission issues. And we'll get into that in a couple of slides here. you can also connect to a device that is across your desk or across the lab or across the world. The You can open up an instance of Python on a Windows laptop and communicate with this Raspberry Pi, and we'll demonstrate that we'll demonstrate that after we work through the exercise here. There's also a USB backend, so this is how like the Pluto SDR connects, and Serial, which is how the tiny IOD no OS devices would typically connect to like an embedded microcontroller here. And then here, just let's take a peek at this code here. So reminder from the device tree, channel 1 is configured as an ADC DAC. So I can import ADI, import all the device classes, instantiate the device, connect to some URI here. And then the commands to set and read voltages are pretty straightforward. It's my device.channel1.raw, so the raw digital value is 1024. So I'm going to set the output to a quarter scale. Then I'm going to read it back. So I'm going to read back the value of channel 1, read back the actual voltage, and then I'm going to read back the scale. So that scale value in millivolts per LSB, and then finally print and then close out my connection here. So this is a lot of words talking about a this is a lot of words talking about a snippet of code. So let's do this in real life. So if we go back over to Kuiper, go back over to your Raspberry Pi here, and we can close out of IO Oscilloscope, and let's open up Thonny. Oh, that's not right. That was the File Explorer. So let's open under Programming, Thonny, Python IDE. Okay, and so let's take some time to explore PyADI IIO's example scripts. So we're going to click Load, and then in the JES Workshop folder, this PyADI IIO folder, this is all of the source code for PyADI IIO. It's the entire repository on GitHub cloned right here. So if we go inside that directory and look in examples, this is a collection of examples for every supported device, and they're all intended to be very minimal, just enough to get to Hello World, grab a block of data from an ADC, write a voltage to a D to A converter, read a single temperature, and so on and so forth. So let's open the example for the AD5592. Okay, and take a minute to scan through the code. It should be fairly straightforward. Okay, sure enough, we open up a connection to the device, we scan through the channels, and we prompt for a voltage if it's an output, and then we read back every channel. And we have to treat temperature a little bit differently, do some different math on that. So we account for that here, and then we print out the read back value. So let's go ahead and run this. Okay, so desired voltage for channel for 0. So let's do 1,000 millivolts, and then enter. And then for channel 2, let's do 2,000 millivolts. And then on the little PowerPoint slide there, it says that 1, 2, 3, 4 will do something interesting. This number also is super handy to use for a combination for your luggage. Okay, and if we look at the output, we see that we've got, so some of the channels are inputs only, and so those should read, so we've got 24 degrees C or 25 degrees C on the temperature sensor. Voltage 0, it is an output, so we have written, for channel 0, we have written exactly 1,000 millivolts, and we read back very, very close to that. So again, this is the value that we wrote. And then if we look at, there should be so I guess voltage 0 was an output only. And then if we look at voltage 1, so that looks like that's probably the input, because this doesn't really correspond. Yeah, this doesn't correspond to anything. So this value is just kind of floating here. And then voltage 2, yeah, so voltage 2 is both an output and an input. So I told it to please give me 2000 millivolts, and lo and behold, I get exactly the same voltage. I don't think that'll always be the case. And then here's a case where we have a small discrepancy. I have written 1, 2, 3, 4, rounded because I've got, I can't hit exactly 1, 2, 3, 4, and what I read back is 1, 2, 3, 1. So there's a small discrepancy between the exact digital value that I wrote to the DAC and the actual analog value that I read back on the ADC. I have 2 error sources there. And again, so these examples are just meant to get you and the customer up and running. So 66 lines of code, including the license at the top of the file here. Okay, so now let's do something useful with that example. So when I was putting together this slide deck, I started with that example and wrote the curve tracer code. And I'd like to take a couple of, let's take, maybe 10, 15 minutes to just sort of explore the code here and ask questions, and we'll try to answer them. But we tried to comment this in a way that makes it sort of readable. So take a while to read through and see if all of your questions that come up in your mind are answered, and if it gives you an understanding of how this code works. And I'll point out a couple of things once we get to analog world. So again, I maintained the initial snippet of code here that prints out all the values. And then this is what I was referring to earlier. Let's take those channel names and let's make them intuitive in our code. So we'll define a couple of constants here. So again, referring back to that LT Spice schematic, I've got a 47 ohm sense resistor, a 47K base resistor. I'm going to define my VBE, makes it easy to change everywhere by defining it once up top here. Then I assign symbolic names to each of the channels here. So my base drive, my current sense, and my VC drive. I can also read out the millivolts per LSB, again, just to make the code easier to read. I forgot why I left this in here. I think I wanted to write a non-zero value at one point. I don't think this needs to be here. And then here is the curve tracer code itself. So just briefly, I'm going to sweep through base voltages starting at 499 millivolts. So a little bit less than a VBE because I want to start out with a very low base current. And I'm going to step up to 2.5 volts in 500 millivolt steps. So I get 6 total runs through the loop here, 6 different curves. And then for each curve itself, I'm going to sweep the collector voltage from 0 to 2.5 volts, and I'll do that in fairly fine steps, in 50 millivolt steps here. And again, just intuitive math here. So I set my collector drive, and yeah, so I set my collector drive based on millivolts. I read back my collector current. I read back my collector voltage. Yeah, so I read back my collector voltage, run a couple of calculations, and I append my reading to a little array here. When I'm all done, I end up with a 2D array of curves, and then I plot it. So again, that's a lot of words talking over code. The best way to learn is just to take a few minutes to study it. But let's run it and see if we get a curve. Okay, lots of debug information printed out in the display here, including what those base currents are. Okay, and there it is. So let's think about where we're at here. We built a simple circuit. We took an example, a PyADI example, and we turned it into a test instrument. So maybe time for a little discussion here. Does this sound practical? Can you think of any other simple customer applications? Obviously this is contrived, and customer applications, while it's easy to do, I guess it's easy to do, like, what is the next step? Aside from just getting the data, maybe the customer is doing something incredibly complicated, but is there one extra step that you can take them down that helps them down that path towards their complicated widget that they're ultimately building. Okay, so we've got a curve up and running. Okay, and now it's time for, okay, so I want, back to PowerPoint. Okay, so here's our PyADI example. Proof of concept. Okay, so now it's time for our contest. So hopefully we've got enough time to spend a little bit of time on this, and so I wanted to put together something that was fun but doable in a short period of time here. And we kind of have two options here. One is just to write a script to blink the light red and green. And a little reminder of what the circuit is here. So output voltage 2 and output voltage 3 has that bicolor LED connected to it. So literally at the end of that script, write some code to set the two voltages in alternate polarity and blink the light. So that should be fairly straightforward. The other one, if you're up for a little bit better of a challenge, or a little bit more interesting of a challenge, is think about that code and how could you get it to plot out beta instead of collector current. So beta is the collector current divided by the base current, and again, that's something that you would normally calculate on a curve tracer by looking at the distance between the curves here. And so I've got one possible solution printed out here, plotting out the transistor beta instead of the collector current. So we'll take a few minutes to work through the contest, and we'll be walking around the room and helping out when necessary. Okay, great. So we've done proof of concept. We've written a couple little snippets there just to test out a few other operations, blinking lights, making some modifications there. So what about our customer? Where can our customer go if we can get them to that point here? So in the case of this curve tracer design, if you've got a venture capitalist banging down your door, then build up 10 units with Raspberry Pis. Never mind the fact that you're going to want to cost reduce this thing. But if you can use this as a means to generate a few pilot runs, then that can come in handy in some situations. You don't have to recompile. You don't have to bring up another tool chain. Just cost be damned for these first couple of prototypes here. If you are sticking with Linux, then migrate to a production-worthy board, like 96 board if you're an Arrow fan. I think we may have some Arrow folks in the room here as well. BeagleBone if you want to support if your customer is dead set on it, or some other Pi alternative that you can actually get these days. Again, another advantage to working in this environment is that driver code applies to any platform. Okay, or if you're cost reducing, heading towards an embedded solution, then build the NoOS example project on an AD ICUP 3029 or one of the Maxim Feather boards here. So we'll show in a couple of slides here that and Dragos is demonstrating this in his NoOS hands-on, that it is possible to take the same exact code that we just wrote for the setup that's in front of you and talk to an embedded controller as well. So with 0 lines of code changed in the Python. Okay, but I want to use, so we alluded to some of those other fancy Python development environments. How would I actually do that? Well, that's where the IIoD server comes in. So the IIoD server exposes devices over a network backend. And what that means pictorially is I can have my circuit and my device running on a Raspberry Pi, and I can communicate to it from my Windows, Linux, or Mac device here. And what's nice about that is, for Python, I can use a much more powerful development environment like Spider that I use, or VS Code or Python. And there's a little reminder here to ask me for a demo. So I'm going to ask myself for a demo. And first of all, just a reminder that, yep, I'm running my curve tracer over here on a Raspberry Pi. So we'll give that a chance to run. Okay, and now this is running in Windows. This is my big bloated Python IDE called Spyder. And it looks like I have a bunch of other stuff open here, but let's open up. I must have closed it here. Recent. Curve tracer. Okay, so same exact code that is on my Raspberry Pi is now in my Windows machine. And what do I do differently? So do I have analog.local here? Let me just remind myself. Yeah. So this code that was running on Thonny is actually pointing to analog.local. So yes, it's talking over a network connection. No, the data never actually leaves the machine. Here, analog.local means something different. So let's actually bring up a PowerShell window. And gosh, I hope that's visible. Oh, size. Oh, yeah, so hopefully that's visible. But I can ping analog.local. So this is, I'm receiving pings back from my Raspberry Pi in exactly the same way that I can ping google.com. So the Raspberry Pi is on the same network as my laptop here. I can Google something, I can ping Google, and I can ping my Raspberry Pi. I've got this network connection established. And then from my Python environment, I've got the same exact code that was running on the Raspberry Pi, now running on my Windows machine. So if we run this, then sure enough, we get exactly the same output. So think about the power of that there. I've got a remote device of some sort, but I can develop useful code in my comfortable environment that I'm familiar with. Spyder itself is also available on Mac or Linux. So again, I've got flexibility in terms of how and where I can develop. But I want to use C++ or C# or MATLAB. That's where the language bindings come in. So libIO has multiple language bindings, C, C#, MATLAB, and there's a couple of other more esoteric ones that are a little bit less documented there. So I've opened up language support for these devices as well. I can use Python because it's easy and cheap and free, and then as I'm moving towards production, I can refine the design, move to C# if I'm doing C# GUI or something of that nature. So we alluded to the fact that we may not want to be spending 40 or 50 bucks on a Raspberry Pi for each of these things. I want to use a couple of dollar microcontroller. And so this is where Dragos's workshop would be extremely useful to take a look at. So the Smart Team in Romania has developed a library called the Tiny IIoD Server, which is essentially an embedded implementation or an embedded emulation of the IIoD server that's running on the Raspberry Pi. And so what that allows us to do is write a Python example that communicates with Raspberry Pi, disconnect the network cable, connect a serial cable to my Maxim development board, and nobody's the wiser, at least not at the application level. So now I can use the same proof of concept code that I wrote on to target a Linux-based device. I can use that to prove out the concept of to prove that my embedded hardware is still working. So again, a nice powerful feature that provides flexibility. Okay, and then finally, porting to a fully embedded solution. And this is where you would get rid of any notion of a server. You would use exactly the same NoOS platform driver, NoOS device driver as the previous slide. I should have pointed that out here. So this rides on the NoOS device driver, NoOS platform driver, but we have this little server. So if the final step is to get rid of the server and write your embedded code. So do all of this in an embedded C program, find some device driver here, and I even found a little feather display board, a little feather prototype display from Adafruit. So again, moving towards a prototype of the fully embedded, cost-reduced solution. Okay, so hopefully that was a useful exercise, just exploring the different ways that you can use these examples. So let's look at some less contrived examples, something a little bit closer to real life than Fred in the shed. So remember this slide from the beginning of the presentation. Hopefully that exercise gave you a little bit more perspective here. The power of being able to grab data from a device arbitrarily and write simple scripts to do useful stuff with it. So let's look at a couple of other examples. If anyone here is signed up for John Kraft's phased array workshop that I think is being offered on Thursday or Friday, that is a perfect, wonderful example. This was a project that John put together and sort of willed into life out of his own interest here. And it's complicated under the surface. It's based on an AD-ALM Pluto. It looks like we're reversed here, which is an AD9361 transceiver chip. There's a couple of other peripherals here. Again, really complicated device. Happens to fall under the IAO framework. And there's plenty of PyADI IAO examples. Normal human beings, non-computer scientists like John and myself were able to get in and do useful stuff right away. There's also a bunch of other peripherals involved. There's the 4159 synthesizer and ADAR 1000 beamformers. And so the way this system was put together is we've got a Raspberry Pi controlling all of these peripheral devices. We've got a Pluto that handles the high-speed RF data capture and all of that business. And how do we tie all of this stuff together? We've got two different Linux machines running at the same time. And really it was because every one of these devices had a device driver, had a PyADI example. We were able to put everything together and come up with this workshop with the hardware for the workshop that John will be presenting here. And this is also where we exercise that ability to develop on Windows and run on the Raspberry Pi. The software for this is non-trivial. It involves calibration and lots of number crunching and things like that. You wouldn't normally think about doing that on an embedded Linux machine. So we developed all the code on a remote Windows machine where things were comfortable. We've got lots of extra processing power. And then finally, at the very last minute, we migrate over to the Raspberry Pi for the workshop. So things run a little bit slower on the Raspberry Pi, but they still run. It's adequately fast. But again, I've got this ability to develop complicated code on a remote host, on a remote computer where I'm comfortable, and then at the very last minute move the code over to the embedded platform. Okay, and just a pictorial of that. Here's what that looked like in real life. So I replicated this in my home lab. This was John's setup here. So it's two ADAR 1000 eval boards, ADF 4159 eval board, a Pluto, everything just wired and hacked together. When we started out here, we had drivers for some devices, but not others. So as we went through this process, the software team developed the missing drivers. Travis helped us out with the PyADI layers for these things. And by the time those were all buttoned up, once the drivers and Python interfaces were there, we didn't have to bug the software department anymore. We were armed and dangerous. And yeah, do you notice a difference between this setup here and the final product here? A lot more compact. Okay, just a couple of snippets of phaser code here. Again, we're not going to dwell on this, just to emphasize that even though I'm working with much more complicated devices like ADAR 1000s, you get the idea. I still name everything. My ADAR 1000, my ADF 4159. I think I have my SDR here for the Pluto here. I set up my beams, my beam element ordering once, and then I never think about it again. I connect to my devices, and that's done. And then I communicate with those devices with very simple language. My SDR, RX local oscillator, and I just give it a number. So same thing with 4159. I want 10.525 megahertz, or sorry, gigahertz in this case, plus a couple of offsets, reduces to a single line of Python code. Very powerful operations in intuitive, simple code. Yet another example. CN569 is a gesture sensor that's based on the ADPD 1080. So what this thing does is I have an ADPD 1080, and under these little shrouds here is the ADPD, I forget the part number. It's an infrared light angle sensor. And there's a couple of ways to implement this. I could write, or we could write, a fully embedded program on the AD-ICU-P3029, the little microcontroller board, and have it output, swipe left, swipe right, swipe up and down. But we split things up a little bit differently. We use the tiny IOD server running on the 3029 board, and we do all of the number crunching on the host PC. So no customer would ever do that in real life. But what it does is it lets the customer hack around. They don't have to call us up to experiment with different algorithms. They get the raw data, the raw readings from the board, and monkey around with it in Python up here. Then at the very last, then as they move down their production path, start moving towards that embedded solution. I love these pictures, by the way. These are light values from the sensor during a swipe. So you notice that we get low values, and then what this is the 4 different sensor values and the sum of those values. So we use the sum of all of the light coming in to say, hey, a gesture happened. And then if you look at the X and Y data, super cool. We start out, these are divided by one another. So we start out with a very noisy low-level signal, but once we know that an event is happening, you notice that the reading gets a lot quieter, and we notice that, oh, the red line sweeps up across the blue line for whichever this swipe is, and then opposite direction for swiping in the other direction. So again, this is the kind of thing that is easy to do in Python. It's easy to hack around and modify algorithms. I can change my endpoints and things like that, but I can do it in a comfortable environment, figure out what I want, and then head towards that embedded solution. Another example, LiDAR platform GUI. So the COS or SDG at the time built up a LiDAR platform for a LiDAR platform to handle these, to interface with these high-speed transimpedance amplifiers for those applications. And the guy that supported this was actually one of my former interns, a really smart guy. I would say borderline brilliant, and he needed a GUI. So we had raw data, we had I/O oscilloscope, but he wanted a standalone GUI that he could pass off to customers here. And so I handed him a Pluto SDR and a few examples of PyADI wasn't in existence at the time, but a few examples of Python talking to I/O devices. And the first day, complain, this is terrible, I can't stand it. Second day, complain, this is terrible, I can't stand it. Third day, the light bulb went off. Hey, I get it, I can talk to the Pluto, now I understand how to talk to the LiDAR platform, and I think after that, it was a day before he had something functional, like a working model with things like, and you notice, IP address, how wide do I want my pulse width, what do I want my rep rate to be, and I get LiDAR pulses out of this thing. And this is a piece of code. It's not very pretty, but you can give it to a customer and say, customer, you put your own pretty face on this, or use this to debug, and then move toward your integrated solution that actually goes under the hood of a car. Yet another example. Todd Feligi is a power-oriented FAE in Florida, and he's working with Eric Weldy on a project to characterize data converter power supply rejection. That is a very important problem because it helps to tease out which power rails on an A to D converter are sensitive, which power rails require an LDO, which ones require a silent switcher followed by one of these super high power rejection LDOs versus power supplies versus supply pins that I can connect up to a switcher, like maybe a digital I/O pin. Not always a straightforward question. So Todd's working on a way to programmatically characterize that. And when I first started talking to him about this, he was collecting data in ACE, manually figuring out what the rejection was, writing it down in a notebook, adjust the abuse frequency or the interfering frequency, take the reading manually, put it down in a notebook, and so on and so forth. Real pain in the butt. So one of the parts that he was characterizing, fortunately, fell into this IAO framework. And I took probably half an hour to write a very simple little snippet of code that doesn't measure power supply rejection. What it does is it's basically a simple network analyzer. So it sends out a tone from an M2K, and I capacitively couple into the input and measure the high pass response. So this isn't what Todd wants. He wants to abuse a power supply rail and capture data and see where the tone is. But topologically, it's the same thing. Set a tone, take a measurement, step, repeat. And that's all he needed to head towards the finish line. A week after sending him this code, he had a working model of the full power supply rejection characterization software. Okay, so again, because it's in this framework, I can write a 20-line snippet of code that demonstrates the concept and say, here, power supply expert, this is what you need to take your measurements and head down towards production. Okay, I think this might be the last example here. There's a paper that Travis Collins put me up to a while back, or suggested that I write something for the SciPy conference. So Christina Shuteu, who I think is attending the conference this week, and I put together a paper on analysis of signal chains using Python. And you can kind of see on the little picture here some very common themes. I've got a remote host. I've got a Raspberry Pi that's talking to, in this case, an AD7124, and snippets that measure the digital filter response of this device, snippets that send out a band of noise to the device and verify its rejection. And all of it is with little 20-line Python scripts, all sort of buttoned up. And again, because things are in a industry standard framework, the complexity is, I don't want to say it's hidden, but it's comfortably abstracted. Okay. All right, so I think we're done with the technical content here. So what's the action item here? So I guess kind of in a nutshell is it's the next time that you're selling an ADC or a DAC or a temperature sensor, one of these devices that connects to a controller or a controller of some sort, see if it's supported in Kuiper Linux and or PyADI. And if it is, run the example yourself. The act of connecting the hardware, running the example, making a simple modification goes a really long way to understanding things and being able to do the next step, which is show this setup to your customer. And then prompt your customer, say, what is just enough software? Like, how can I take this data converter and run one extra little piece of analysis that will help show the value proposition, that will help you along with your development process and get you closer to a design in. And if you're in a mixed signal dry spell as far as selling products, pick an interesting example and play. There's a couple of examples that we've linked in this presentation, and that final paper that is meant to be a tutorial example. Okay, final reminder to beat a dead horse. Most of us are not going to instantly turn into software engineers. Proficiency really comes from getting your hands dirty, corrupting SD cards, seeing this Raspberry Pi screen of death, breaking stuff, and then recovering. If you crash an SD card or corrupt it or something like that, you're 5 minutes away from burning it and basically resetting to a starting point here. And again, every time you encounter a part that's supported by Kuiper, run the example and show your customer how to do it. Acknowledgements. 99% of the work in this deck is done by these folks that contribute to the various projects here. We've got the libiio, the PyADI-IAO, multiple contributors, but especially Travis Collins, who architected this thing and sort of made it what it is. And of course, the Kuiper Linux itself, especially Stefan Rouse, who is running this project. And of course, our patient reviewers that sat and listened to me yap for 3 hours on a Friday afternoon. Adrian Flanagan, Yasmin, John Kraft, and Deepak Patel.